Hello, everybody. Welcome back. And today we are going to be looking at systems in control theory. So when developing control systems, you would hear the word systems a lot. Control systems, the plant system, this system, that system. So what are these systems? A system is basically a collection of different parts. They're interconnected to form something bigger, something more complex. And in engineering generally, these systems manage complexity by breaking large projects into manageable parts. So if you have a complex operation, you can break it into different smaller parts that can be easily managed. Now, these systems, such as control systems, are specialized and they are designed to meet certain performance requirements. So control systems generally want the overall system to perform in a certain way, perform better, perform in a more optimized manner, perform in a more efficient way. Now, the system has many components. The first is the process. There is a process that takes place within the system. That process gets an input and it gives you an output. So the input goes into the process processes the input and then gives you the output. In some instances, you have a form of feedback where the output is measured, and that will determine the next set of inputs that will come into a system. And these systems can have multiple inputs and multiple outputs, or can just have a single input and a single output. So why do we even need to define these systems? Why are we talking about them? Now, when you're working on a big project that is complex, you need to divide it into smaller subsystems. And you have various specialists that work on the different components of the system, like sensors, the actuators, and the controllers. So the systems generally exist at three different levels, right? You have the components, which are the basic form of the system. Now, these components form subsystems, and these subsystems come together to form an overall system. So an example is a car braking system, right? All we know that when we're driving is we hit the brake and the car stops. But there are many interdependent components and subsystems that make up this car braking system. And you can see this picture that shows the car braking system, but it has many components and many subsystems that make the braking possible. Now we have systems that are natural, such as our plants, and these plants regulate themselves based on environmental conditions. For example, photosynthesis, which is the way plants make their food. The input are the sunlight, the carbon dioxide, and water, and the system process converts does the chemical conversion inside the leaves, and the output eventually is oxygen and glucose. There is also a feedback control where you have the stomata, which regulates the carbon dioxide and water loss. Now, in addition to natural systems, you have our artificial or control systems. An example is the smart irrigation system, which uses sensors to detect soil moisture, maybe regulate watering, how much water is put into the soil. You also can have greenhouse climate control systems that optimize plant growth. The feedback they're getting there is the temperature and humidity. Now, control systems generally, whether it's in engineering artificially or in nature biologically, need to respond to inputs, process them, and adjust outputs accordingly. So an example that we give the smart irrigation system, you have a set point, maybe the amount of water you want to be maintained in the soil. You have the irrigation system, which is the process, and the output is the water, which is done using pumps. Then the feedback would be the soil moisture that you acquire. Now, when you are dealing with systems generally, particularly in engineering and control, you need to represent these systems in a certain manner. And these representations need to have precise descriptions so that they can be designed and controlled properly. Now, this representation is done using models, and these models describe how the system responds to the inputs and what kind of outputs the system gives. Models help us understand, predict, and analyze system behavior. Now, these models can be physical models and they can be mathematical models. In physical models, they are basically real-world representations. You actually build these physical models. For example, if you have a car suspension system, the physical model is a scaled down setup of that car suspension system. So physical models are things you build, but they are smaller and less complex versions of the real system. You can see here there is a physical model of a control panel. It's not as complex as the actual control panel for a bathroom shower system, but it gives you an idea on what the system should look like. Then this is a physical model of a factory. You can see it's not as complex as the factory, but it's an actual representation of what the factory would look like. Then you have mathematical models. Mathematical models are equations that describe the system behavior. So, of course, they are easier and cheaper to develop than physical models. You don't have to buy anything to put it together. You just need to analyze and see if you can bring out the equations that describe the system behavior. Now, going back to our car suspension system example, the mathematical model can be a differential equation describing motion. And this is a mass spring damper system, one of the basic models in engineering design. And you can see this is just a free body diagram of what the model represents, but these are the differential equations that describe the model. So these are the mathematical models. Now, mathematical models in control systems are widely used because they define the system dynamics using these equations. It helps you design these control systems more effectively. Now, common representations of these systems are your differential equations, as we mentioned earlier, which are equations that describe the behavior of the system over time. Then you have transfer functions, which describe the behavior of the system in the frequency or Laplace domain. And also you have state space models, which describe the system using matrices and equations. And all these representations are important in control system design because when you are developing these control systems, you are not working with the actual system. You need to work with the representation of the system and tune the controller to make sure it works properly before you deploy it to the actual system. So in subsequent sessions, we'll be looking at how to model some of these systems, particularly using transfer functions and state space, and how you can design these control systems using these models. Thank you.